All right. Hello, CPPCon 2020. I'm Ben Sachs. For those of you who don't know me, my company, Sachs & Associates, offers training in C and C++ for companies all over the world. And I'm going to be talking today about customizing dynamic memory management in C++, in particular, but not exclusively for embedded systems programming. Feel free to ask questions during the talk, but please understand we're on a something like a 10 to 15 second delay. So if it doesn't sound like I get to your question right away, that might just be because it hasn't appeared in my on my screen yet. So yeah, just give me a moment. I will do my best to answer questions as they come up. Anyway, so let's go ahead and get started. Your first question might be dynamic memory management in embedded systems. I just don't do that. My system is not doesn't use any dynamic memory, and for a lot of embedded systems, that's true. And there are reasons why that's the case, because the default dynamic memory allocator in C and C++ often has some characteristics that don't make it well suited to use in embedded systems. It can be slow, and more importantly, it can be how long it takes can be non-deterministic. So in some cases, you want to get an answer within a certain amount of time, whether it's yes or no. They also run the risk of fragmenting memory over time, where the longer the program goes on, the harder it is to find suitable pieces of memory for different size objects. And for embedded devices, which are designed to run for indefinite periods of time in a lot of cases, something that degrades over time is not good. So there are a lot of embedded systems that just avoid using dynamic memory altogether. But what I'm going to show you here is you don't necessarily have to forego all use of dynamic memory. You just don't necessarily want to be using the default dynamic memory allocator to do it. If you write your own memory allocator, if you customize how the allocation system works, you might be able to get something with performance characteristics that are more suited for your application. Okay. So first off, let me start off, just make sure we're on the same page. When I talk about objects, objects in C++ have a storage duration, which is the lifetime of the storage that contains the object. And it comes in three flavors: static, automatic, and dynamic. Static storage duration is for objects that are created when the program starts up and last for the duration of the entire program, which for a lot of embedded systems is going to be just indefinitely. A lot of embedded systems don't shut down the same way that you close Microsoft Word. So for embedded systems, static storage duration is often essentially the entire life of the program. Essentially indefinite. For objects with automatic storage duration, this is what we think of when we think of objects created on the stack, function parameters, variables that are local to functions, things like that, where the memory for them is allocated on the stack at the point when control enters the function call, and it lasts until control leaves that function call. So those objects are created, they stay around for however long they're needed to for that function, and then they go away. And the third category, which is what we're going to be mostly talking about today, is dynamic storage duration, where the storage for an object is allocated when you ask for it. When you manually do something to request the memory for an object, and you have that memory available to you until you say, I'm done using it. And you call a deallocate function to return that memory to the general store. So in C, we would typically allocate memory dynamically using malloc and free. So you would call malloc, you'd pass it the size of the object that you're trying to allocate memory for. It would return back to you a pointer to a dynamically allocated block of memory that you could then use to store your T object, and you'd use that until you were done with it. And when you were finished, you'd call free, pass it the pointer that you received from malloc, and that would release the memory back into the system. In C++, we do dynamic memory allocation a little differently. We typically use new expressions and delete expressions. So instead of calling malloc, we write new T like this, and that returns back a pointer to a T object. And again, we can continue to use that T object until at some point we say we're done using that memory. We write delete P, and that frees up the memory for use by some other object. And this doesn't look that different from malloc and free. So you might ask, why did C++ need to introduce new and delete, given that C already had malloc and free? And it turns out it has to do with constructors. Malloc is a one-step process. All it does is dynamically allocate memory and then return a pointer to it. It hasn't done anything to the contents of that memory. New is a two-step process. First, it allocates memory just like malloc does. That's the first step. But it has a second step that malloc doesn't have, which is to call a constructor for the object that you're trying to create in that memory. Make sure that an object of type T is actually created there appropriately. So if you were to break down a new expression, look at what the compiler actually generates behind the scenes for a new expression, what you would see is that this new expression would translate into something that looks internally kind of like this. So this is step one, where we call this function called operator new. We pass it the size of the object we want to allocate, just like we did with malloc. And the compiler will automatically generate code to convert that to a pointer to a T and assign that to P. That's basically the same as what malloc did, just a little bit using slightly different words. The second step here is to essentially call a constructor on that object that we've just allocated to initialize it. Now, you can't actually write code like this. You're not allowed to just explicitly call a constructor on the object that a pointer points to. So this is just an imaginary notation for the sort of thing that the compiler is doing internally. By the same token, a delete expression really translates into something that looks kind of like this. It checks to see, is the pointer a null pointer? Deleting a pointer is always safe, or deleting a null pointer is always safe. It just does nothing. But if it's not a null pointer, if P actually points to something, first we have to call the destructor for that object to clean up any resources associated with that object. Then we can call operator delete and actually release the memory that was used to create that object, to store that object. Now, unlike the previous slide, you can actually write an explicit destructor call like this. You almost never want to, because usually if you just write this, well, the compiler is already planting calls to destructors automatically for you. And what will wind up happening is that the destructor gets run twice, which is usually not what you want. So outside of some very rare circumstances, you don't actually need to call the destructor like this. Okay, question. How can you observe what the compiler is doing? Is there some compiler flag or similar to output to the intermediate code? Yeah, when I'm talking about this, what I'm saying is, when I say what the compiler is doing, I'm referring to the assembly code that gets generated that is then loaded to the device, that the device would actually execute. So when you compile a C++ program, the compiler turns that source code into object code. That object code is then linked together across your several different source files to form your executable. And that's what is actually running on the device side. If you look at what's generated there, what you would see is instructions that are doing the equivalent of this. I've rendered it in a C++ syntax to make it a little easier to read, but often the generated assembly code has comments in it that the compiler just plants there, and so you would see that at this point it would call a function, and that would have some numeric address for it, and then off to the side there might be a little comment that says t : tilde t. And that's what I'm referring to when I talk about what I would look at to see what the compiler is actually doing here. Is p not equal to null putter generated? Is that p not equal to standard null putter generated? Yeah, the idea is this delete expression translates into something under the hood that looks like this. You write this code, and what the compiler does is it takes care of checking to see whether the pointer is null for you. If the pointer isn't null, then it has work to do to delete the object, to call the destructor on the object that p points to, and then the last step is to release the memory associated with p. So a new expression, as I showed you a little bit ago, a new expression allocates memory, that first step of the allocation process, by calling a function called operator new. It's literally the name of the function. Now, C++ provides a default implementation for operator new, and it looks like this. It's a function named operator new that takes a single parameter of type size t and returns a pointer to void. And n is just the size of the amount of storage being requested in bytes. A delete expression also has a corresponding operator delete function that looks like this. That also has a default implementation in C++. So it looks like the function is called operator delete. It takes a pointer to void, returns nothing, and the function is declared no except because delete can't throw exceptions. You will never see an exception thrown from a delete expression. So now, in a lot of implementations of C++, operator new will actually call malloc, and similarly, operator delete may very well call free, which means that their performance characteristics are going to be similar in many cases. Those default implementations are the ones that we were concerned about being too slow, being too non-deterministic, or causing too much memory fragmentation that might not be well suited to an embedded application. But what we can do in C++ is that C++ lets us replace the implementations of operator new and operator delete with our own implementations for those functions. This is something you can't do in C. You're not allowed to replace malloc and free, but you are allowed to replace what operator new and operator delete do. Now, the replacement functions look exactly like the functions that they're replacing. You're just writing them yourself instead of relying on an implementation provided by the toolchain vendor. Now, there are some restrictions on what these replacement functions can do. So here is the operator new function that you would write would look like this, and the required behavior is it either returns a non-null pointer to suitably aligned storage, or it throws a bad alloc exception. Now, I realize, wait, it throws a bad alloc exception? I don't use exceptions in my embedded software. That's not going to work for me. I realize that that question is going to come to your minds quickly. Hold that thought. We'll get there. But for right now, I want to just show put that to the side. I want to just show the mechanics of how replacing operator new works. And then we'll talk about how to make sure that it fails in some other way that's more acceptable for an embedded system. All right, so if I were to write an operator new, the basic structure for replacing operator new is going to look something like this. You're going to have your function operator new that you write. You'll go through some process to find a suitable piece of memory for an object of size n. And this myAllocator function, this just finds memory in whatever form is appropriate. And we'll talk about some algorithms that you could use for this in a little bit. But tries to find memory for the object. If it wasn't able to find memory, it returns a null pointer, in which case operator new, in this case, throws bad alloc to report the failure. Otherwise, it returns back the pointer that the allocation function provided. By the same token, an operator delete replacement generally looks simply like this. There isn't as much work to do because delete doesn't report failures. It doesn't have any way of, a delete should never fail. So it just calls whatever function is necessary to deallocate the memory, and then it's done. So here are some very simple replacements that I could write for operator new and operator delete that are designed to track the number of allocations that haven't been deallocated yet. It gives me a running count of how much memory has been allocated in a rough sense, because objects are different sizes, over the lifetime of the program, so that, well, if I reach the end of the program and that number isn't 0, that's a pretty good indication that there's a memory leak somewhere, for example. I realize that in an embedded system, you often don't reach the end of a program, but you can still have a situation where what you see is that the trend is just going up like this, and that's often a bad sign. Usually you'd expect it to level off after a while. So this is what the implementation looks like. We have a static global counter, just deletes left to do, starts out at 0. Each time we call new, we increment that number of deletions left to do. And then when delete gets called, we decrement that number of deletions. So each time we call new, we add 1. Each time we call delete, we subtract 1. That gives us our running count. Now, it turns out actually that replacing new and delete is a little bit more complicated than I just showed you, because there are actually multiple versions of operator new and delete that the compiler might use. So there's one version that looks like what I just showed you that takes a single parameter of type size t. There's a second version that takes a size t and an align val t that represents the alignment requirement of the memory being allocated. And so behind the scenes, the compiler might translate this into a call to either the 1 argument operator new or the 2 argument operator new. And so what that means is if you replace one, you almost certainly want to replace the other one as well. And in many cases, you'll replace them by both having them call the same implementation function. There's not much work involved. It's just something you have to remember to do. There are actually 4 versions of operator delete that a typical delete expression might use. So there's a delete that takes a pointer to void, a delete that takes a pointer to void and a size, a delete that takes a pointer to void and an alignment, and then one that takes pointer to void, size, and alignment. And again, a delete expression, depending on which tool chain you're using, a delete expression might invoke different ones of these functions, and you need to just be prepared for that. So, for example, the default the operator delete that gets called by a delete expression in general on current versions of GCC, I've found to be different from the one that gets called by Visual C++ by default. So if you replace any of your operator deletes, you probably want to replace them all. Yeah, question. Yes, there was a good point. This increment should actually be done down here. It's true that we should be doing that increment after we've already determined that the function is going to successfully allocate memory, because there's no more memory to delete if we actually wind up throwing that alloc instead. Thank you for catching that. I will. I'll have that changed in the official slides that get posted for this. Shouldn't the argument to new go before T? Okay, so what you're seeing here is not an argument to new exactly. This V here, the argument is being passed to the constructor for the T object. So that's a constructor argument, not an argument to operator new. These values, the size and the alignment, are being supplied automatically by the compiler when you write a new expression like this. The compiler knows internally what the size of T is, what the alignment requirement of T is. It fills those values in automatically. Now, in a little while, we're going to see that there is actually a way to pass parameters to operator new, but it looks a little different than that. Okay, so those are the steps that you would need to go through if you were going to replace the global operator new and operator delete. Now, actually doing that, shouldn't the overload resolution cover not changing the other new and delete types, assuming you don't use the other new and deletes? Yeah, I can see why you would think that the rules of C++ say that effectively it's as if these functions are always declared, all four of them, in which case, whereas, so normally overload resolution would say if you only declare one of them, there'd only be that one version. But in fact, the way that operator new and operator delete are specified is a little different. The standard says it's as if these declarations always exist. So overload resolution wouldn't do the job by itself in this situation. I discovered that this was necessary to do because I had the same thought at one point, and I went to write the code, and I was surprised when it didn't call the function I expected it to call. All right, so replacing those global operator new and operator delete is what you would need to do if you wanted to write a general purpose memory manager that could handle memory requests across the whole program. You can do that, but that is kind of a challenging thing to do, and also have it fit within the performance requirements that we have for embedded systems, because it needs to be able to handle memory requests of all kinds of different sizes. And one of the reasons that they didn't choose to make the default memory allocator slow just because. They wound up, the algorithm that's used for the global memory, for the default memory allocator, is slow because it has to take into account the possibility that it could be allocating any size of object. Can you mark some of the delete new operators with equal delete to prevent the compiler from using them and force the versions that you like? I believe when I tried that, I found that the compiler generated code that the compiler would generate complaints that said, the operator delete I'm trying to call here is deleted, not, oh, I noticed that that operator delete is a deleted function, and I'll call a different form of delete. But I'll admit that when I did this some time ago, my memory's a little blurry about that. So if you are going to try and get a global memory manager suitable for embedded systems up and running, there are people who make these things professionally, and that's something you might want to look into before you actually go ahead and write your own, because they are quite complex things to write. That said, you might not actually need a global memory manager, and here's what I mean by that. In a lot of applications, the dynamic memory allocations are focused on just a few types. That is, you might be allocating a lot of different kinds of objects, but what you would see is you have 2 or 3 of type A, 2 or 3 of type B, and then a million of type C. It's not uncommon to see that in an application, most of the dynamic allocations are done for just a few types. And so if you can write a memory allocator that just works for those specific types that you allocate frequently, you can get a lot of the benefits that you would get out of replacing a global memory allocator, but without the complexity of necessarily having to handle requests for memory of any size, things like that. And you can then for the other types that you're not worried about, you could either fall back on the default memory allocator, or if you're running an embedded system, you could just deal with those the same way that we typically deal with objects that we would like to dynamically allocate but can't in an embedded system, and make them global, allocate them statically somehow, things like that. It turns out there's actually a really nice, simple way in C++ to replace the new and delete for specific types without doing anything to affect how new and delete work for other types. You can declare new and delete as members of a class like this. Is the type of object or the size of object that is of concern? Is it the type of object or the size of the object that's of concern? It depends on what you mean. I'm not entirely sure. So when you replace operator new and delete, when you write them as class members, you're writing them for a specific class. So they really will work only on that one class type. Now, the objects of type T are always going to be the same size. So what you could do is that if it turns out that objects of type T and type U and type V are all of the same size, you could write it so that the class-specific new and delete for T and U and V all pull from the same memory source on the back end. But so that is a technique that you can use. I'm just going to show it to you for one type, but it's relatively easy to generalize to use the same pool for several types. Okay. JMalloc TC implement new with a hierarchy of memory pools to minimize fragmentation and improve allocation speed. Are there gotchas that render them inappropriate for embedded systems? I admit I'm not familiar with those specific functions, so I have not seen them. I haven't tried using them in an embedded system, so I'm not sure how they would perform. In general, my understanding is that when you are allocating from multiple different pools, not avoiding all fragmentation tends to be very difficult. But I'd have to look at the specific algorithm here. If you were to derive a class from T, should the derived class implement operator new and operator delete. It doesn't need to, but it can. And often I think it would. Usually when I create a derived class from something, I almost always find that I'm adding data members in the leaf classes of the hierarchy. That is the derived classes that don't themselves have any other derived classes. Usually that's where I find I put my data members, which means that the size of a derived object is not going to be the same as the size of a base object, in which case, the amount of memory you would need for a derived object would be different from the amount of memory that you would need for a base class object. But you could write the operator new for a base class to simply allocate a size that's suitable for any of its derived class types, for example. All right, so you can write operator new and operator delete as class members like this. These have the same signatures as the global operator new and delete that we saw before. And what this does is, when you write new T, the compiler first checks to see, is T a class type that has overloaded operator new and operator delete specific for that class type? If it is, use the class-specific versions of new and delete rather than the global versions. For all other types that don't have class-specific new and delete operators, just use the global ones. The rest of it's unaffected. Okay. Yeah. Is there a way to defragment the existing objects on the heap? My understanding is that that's complicated because it's tricky in most situations because you can't move any of the objects, any of the memory that's actually being used. I can explain that a little bit more at the end, but yeah, I'm not going to say it's impossible, but I haven't seen it done. If custom operator new received arena allocator as argument, how can I pass the same allocator to corresponding delete? I'm sorry, I'm not sure what arena allocator means. I think that the answer to this question may come up a little later, though. So I'm going to proceed on for right now, and maybe that question will come up. Does the polymorphic memory allocator help with any of this? The standard polymorphic memory resource. Let me think. The polymorphic memory resource, I believe that that's actually at a different level. I want to say that that you could use the PMR stuff to implement new and delete, but let me think about that. It's been a while since I've done anything looking at the PMR resources, so I would have to think about that. But my understanding is that that's designed to solve a somewhat different problem of, I want to have many objects of the same class type, and I want to be able to use different kinds of allocators with them, as opposed to baking the allocator into the type the way that we do for STL container classes. Okay. So when you declare operator new and delete as class members, they automatically become static member functions. Doesn't matter whether you use the keyword static to declare them or not. They are static member functions. They have to be. Which means they can't be virtual functions, because as static member functions, they have no this pointer, and the this pointer is how a virtual function knows what type it's actually being invoked on. in relation to my previous question of derived class from class T, if the derived class has its own new and delete, should they in turn call the base class T's new and delete? I wouldn't think so, because I would think that the memory for an object, for a derived class object, is typically going to be allocated in one chunk that would include the base class subobject, as well as all of the other data members added by the derived class. So I would think that you would just be allocating one chunk of memory for both the base class subobject and the additional data members, rather than calling the base class's operator new. But not to say that you absolutely couldn't, just I can't think of a reason why you would. All right, so what do we actually do with those operator new and deletes? We can't, now that I've told you that we can provide them on a class-specific basis, how do we write class-specific operator new and delete in a way that are suitable for use in embedded systems? So the basic strategy that you often see employed is to reserve a number of memory blocks ahead of time, essentially at compile time. So at static memory or static allocation. Each memory block is suitable to hold a single object of type T. And then those blocks are organized into a linked list. I'll show you exactly how this is done in just a moment. But the idea is that operator new takes the first block of memory off of that list and uses that as the memory to hold a T object that you just allocated memory for. And then delete just takes that block of memory and returns it onto the front of the list. And now it becomes, and now it's again free for use by any other T object that needs to allocate memory. So the way that this works, it actually solves a lot of the problems that I talked about earlier with the general dynamic memory management. It winds up being fast because allocation and deallocation are basically linked list operations. They both involve only a small number of pointer operations to take a block off the list or move a block back onto the list. It's deterministic because the worst case runtime is constant. There are only two cases. Either there's memory available, in which case you take the first block because all the blocks are the same size. They're all equally good matches for the size of memory you're being asked for. Or there's no memory available, in which case you return failure. Memory fragmentation isn't a problem because the blocks are all the same size. So there's no risk that by pulling a little bit here and a little bit here and a little bit here, you'll wind up with memory broken into small chunks that none of which can actually hold a T object. Okay. So we would implement it in a way like this, where we'd use this union type avail block, where each avail block has one of two members, either a pointer to the next available block or an amount of memory that is the size of that block. And really, the memory is is only there to ensure that each block is large enough. Basically, when the block is available, we care about the next pointer. When the block is in use, we care about the size of this memory being large enough to hold a T object. So we want to, once we've created that block type, we then need to set up all the blocks so that they form a linked list. And we can do that by placing those blocks in this struct avail list and writing a constructor that assembles that causes each block to point to the next block. So inside the avail list constructor, it just goes through the list of blocks, makes each block point to the next block, the I+1 block. And then at the very end, there's the last block points to null. At that point, we're out of memory blocks to allocate. And so we would, if we use this to allocate or to implement an operator new for a type T, it might look something like this. We'd have the avail list declared as a static object. It's called T list here. What operator new would do is pull look at the head of the list of available blocks, find if that pointer is null, meaning there are no available blocks, or, and this is just a safety check to make sure that we're not allocating an object of the wrong size somehow. The compiler should protect us against this, but this is just a safety check that we can have in here. If either of those conditions isn't met, throw bad alloc. And again, we'll talk about other forms of failure that could come up later on. But if not, if these aren't the case, then we can successfully allocate the memory. So take the head pointer off of the, remove the head of the list, and go back to, and return the pointer that we just got, the first block off the list, as the place to construct the object of type T. And then the corresponding operator delete first checks to see, is the pointer null? If so, just return deleting null does nothing. Otherwise, convert the pointer that we got, the pointer to void, into a pointer to an avail block here, and put it back on the front of the list. Set it up so that it points to the current head of the list, and then it becomes the new head. Now, on paper, that implementation there looks like it should work, but it's actually more complicated than that because we need to consider the problem of storage alignment. So types in C and C++ have alignment restrictions that require them to be allocated on certain memory boundaries. So a lot of platforms, ints have to be allocated on 4-byte boundaries, doubles have to be allocated on 8-byte boundaries. These alignment restrictions depend on your specific platform, so you don't, these aren't guaranteed, and it might require 8-byte alignment, it might require only 2-byte alignment. Depends on the platform. But your platform very likely has some restrictions on these, and if you create an object allocated without the proper alignment, the result is generally undefined behavior. All right. Come on. So, before modern C++, there wasn't really a portable way to determine the alignment restriction of a type. So usually the solution to this was to include types with very strict alignments in the union that represented an individual memory block. The idea was this union then has to have alignment as strict as those types. So we'll throw in the types that we can think of with the most strict alignment, and that'll probably work. And usually it did, but it wasn't guaranteed. Now, in modern C++, the expression align of T can be used to determine the alignment restriction of type T, of a type T as a number of bytes. So you can use this align of T to get the number of bytes of alignment that something needs. And then you can declare an object with align as to say, align this value so that it is so that it has this alignment restriction, the same alignment restriction as an object of type T here in this case. This makes sure that our available list blocks are always aligned in such a way that they will work for type T. So, question, is overriding the member function new hostile to the standard library allocator model? The standard library allocator is I'm trying to, so if you wanted to use this system with the STL containers, I would expect that you'd have to write not just the operator new and operator delete, but also an allocator that's specifically used, that could specifically deal with those types. I believe when I've looked at the general purpose default allocator before, it was I believe it uses member functions internally to do with names like construct and allocate instead of new. So I don't think it would cause a problem with that, but I will try and check on that for you if you come and see me after the talk. Should that be a reinterpret cast on slide 35 rather than a static cast? Usually converting between pointer types is a reinterpret cast, but you can turn a pointer to void into a pointer to some other pointer type using a static cast. That has a slightly different rule. Okay, so we can use this approach to make sure that our memory is properly aligned for objects of type T, or actually you can just give align as the name of a type and write it this way instead. Either way, our available blocks should now be aligned in such a way that they can properly store T objects. So there's also operator new and operator delete are actually not used when you allocate arrays like this. There's a separate function, operator new square bracket, and a corresponding operator delete square bracket that get called in this case instead. So this expression is actually going to translate into something like this, where it calls operator new square bracket under the hood, and then goes through each element in the newly allocated array and constructs an object in that memory. Again, this syntax wouldn't actually work if you tried to write it, but this is just an imaginary notation for what the C++ compiler might be doing under the hood. By the same token, an array delete expression, delete square bracket P, translates into something that looks like this. Checks to see is the pointer null. If not, go through the entire array in reverse order, destroying each element, and then release the memory associated with the entire array by calling operator delete square bracket. So you can also make operator new square bracket and operator delete square bracket class members, just like you can make operator new and operator delete class members. This is something you are allowed to do, in which case an array of type T would be allocated using this operator new square bracket rather than the global one. That said, this is a little trickier because it's hard to, this pool allocation system that I showed you works well for single objects of type T. It doesn't work well for arrays because the entire array needs to fit within whatever block you choose to allocate. And the standard doesn't give us any way of saying, do this, but only let me allocate up to 10 of these things at once. You have to be prepared to deal with any possible size array. So it's difficult to bound operator new square bracket and operator delete square bracket for this kind of type. Now, that said, there are a lot of types that you're probably not going to allocate in arrays. So for many cases, what you can do is you can protect yourself against that by declaring operator new square bracket and operator delete square bracket as deleted functions for a type. And then you won't accidentally call the global operator new square bracket for this type when what you thought you were getting was the class-specific new. This should protect you against that. Wouldn't operator delete need to be declared virtual, or is that implicit? The fact that your destructor is virtual takes care of that, essentially. The destructor figures out which type it's being called on, and then behind the scenes, the delete it's taking care of the delete according to the dynamic type of the object. So now to go back to that earlier problem that I mentioned, where we don't want to throw a bad alloc exception on an embedded system generally. We want to fail in some other way, because exception handling often raises significant performance concerns on embedded systems. So the standard also provides us with another version of new called no-throw new, which is a version of operator new that takes a size t and then this object of type no-throw t, reference to const no-throw t. What's a no-throw t? It's a made-up type of object that only exists to differentiate this operator new from the operator new that can throw. And this version of new is also replaceable, and it has a different required behavior. Return a non-null pointer to suitably aligned storage, or return a null pointer. So this is something that we can generally use on embedded systems a little bit more easily. So the non-throwing version of operator new, you write the call to it like this. When I said earlier that you can pass arguments to operator new yourself, this is what I was talking about. So here, this expression looks a bit odd, because what's happening is we're using new. Stood no throw here is a object of type no throw being passed as an argument to operator new. Then create a t object in the memory that we allocate and construct it by calling the constructor that takes a v, the t constructor that accepts an object of whatever type v is. And then you just use that memory as you would, and then delete the pointer when you're done with it. This version of delete is actually the same version of delete, doesn't have an extra argument. It's the same version that we would have used with the throwing version of new. And that's generally not a problem. Basically, operator new delete needs to be written to clean up after both versions in many cases. But usually that's not a problem, because the two operator news, the only difference between them is the fact that one reports failure by throwing an exception, the other reports failure by returning a null pointer. So they often have basically the same implementation underneath. They both pull from the same memory pool. That said, it turns out there is actually a version of operator delete that does take an object of type no throw t. Now, that's a little weird, because even the version of operator delete that we had before never threw exceptions. It was already declared no except. So why does the standard feel the need to add this one? Here's what's going on. So I mentioned before that a new expression translates into something like this two-step process where we call operator new to allocate the memory, and then we construct an object in that memory that was allocated. Using the no-throw operator new, like we do back here, that ensures that step one here can't throw exceptions. Being out of memory doesn't cause us to throw an exception, it just returns a null pointer. Step two, on the other hand, a constructor could still fail by throwing exceptions. If that happens, there's this interesting problem, because we've just allocated memory here. This constructor throws, where do we get the chance to delete that memory and clean it up? I'll get to your question in just a moment. The purpose, this is what the no-throw operator delete is designed to solve. So A no-throw new expression, if you really look into it, it would translate into something that looked like this. First, call operator new. Check to see if we got back a null pointer. If so, the allocation failed. We're done. Otherwise, go ahead, try and call the constructor on that object. If we fail by throwing an exception, catch that exception, delete the memory that was allocated up here, and then rethrow. So there's this intermediate step of the compiler takes care of making sure that in the event of no throw new being used, even if an exception is thrown elsewhere, it'll still be cleaned up automatically. So what that means is operator new and delete are always paired like this. If you have an operator new that takes a certain set of arguments, it will find the operator delete, that the compiler will find the operator delete that takes the same set of arguments and pair them up in this situation so that if the constructor fails by throwing an exception, the paired operator delete gets called to clean up whatever the original operator new did. What that means is that anytime you write a version of operator new, you want to write a matching version of operator delete that's paired with it, that takes the same set of arguments after the first, that can deal with exceptions thrown by, that is meant to clean up memory in case your constructors throw exceptions. Now, I realize on a lot of embedded systems, your constructors won't throw exceptions, but it's not that hard to write. It's often only a few small lines of code, and I generally think it's better to be safe than sorry in this sort of situation. So what I want you to take away from this is you can implement dynamic memory management systems that are well suited for use in embedded systems. The available list system is one place that I see a lot of systems use. It's often a good place to start, not necessarily the only solution you can use. You can use the class-specific operator new and operator delete to customize dynamic memory allocation for specific types and optimize the allocation of those types specifically. But when you replace operator new and delete, remember that there are certain requirements that the replacements have to meet. Okay, that brings me to the end. I will stick around to answer questions. I'll answer a question in my remaining time, and then I will be available in Remo briefly to answer questions. I say briefly because I have another thing happening in the next time slot. But feel free to come and ask me questions outside of this session if there are any that I wasn't able to get to. And otherwise, thank you for coming. I hope you enjoyed it. Hope you find it useful. Enjoy the rest of CPPCon. Okay. The question, isn't a union taking care of alignment requirements? What I was showing back here this is including these elements in the union, the double and the size T, makes sure that this available block is aligned in such a way that it has alignment suitable for a double or suitable for a size T. That's a way that ensures that that alignment up to whatever alignment is required by a double or a size T is there. But it's not guaranteed that that's the strictest possible alignment you could have in your system. It might be that there's some type in your system that has a more restrictive alignment than a double, maybe a long double, for example, in which case this block would not necessarily be aligned in such a way that you could allocate a long double safely. So often this would work. Often for most of the objects that you would allocate, this approach of including extra types in the union would generally work, but it wasn't guaranteed. If you wanted to make sure that the object was aligned as it was, that it definitely had whatever alignment T required, you could use this approach. This also has a nice other benefit that it means that you're no more strictly aligned than a T requires. So it may very well be that a double has 8-byte alignment, but a T only needs 4-byte alignment. You might be able to use memory a little bit more efficiently that way. Okay. Question: the stood no throw T seems like a tag type. Yeah, it's very much like that. Yeah, it doesn't really mean anything other than I'm specifically trying to call the version of operator new here that doesn't throw. Yeah, so in that case, in that sense, it's very similar to the tag types that you sometimes see used in certain container types. I see this used in I believe the Boost intrusive containers do this. You also see this done for implementing the algorithm, the STL algorithms, in such a way that they are more or less efficient for different types of iterators. That they're as efficient as they can be for the appropriate type of iterator. If you compile with exceptions turned off, will the compiler then call the no throw operator new without using stood no throw? I believe that's what most platforms do, but the standard doesn't actually say that you're allowed to turn exceptions off. That's an option that a lot of compiler vendors provide, but as far as the standard is concerned, exceptions are mandatory. They have to be in the language. So as soon as you turn that flag on, you've kind of stepped outside of the bounds of what the standard guarantees, and then it's just up to whatever your specific toolchain vendor chose to do. So I believe most of them translate operator new into the no throw version of new, but there could be implementations out there that would simply disable this version of new, treat it like a deleted function, and instead force you to call this if you really want the no throw version of new. Okay, I'm going to end here at this point. Again, thank you for coming. I hope you enjoyed it. I will try and answer a few questions in Remo either now or after this, or after my next session. But otherwise, thank you for coming. Enjoy the rest of CPPCon.